In the direction of Sagittarius, the word darkness is almost misleading, not because the place is empty, but because it is too crowded, too hot, too dust-veiled, and too violent for ordinary sight to survive. In the direction of Sagittarius, behind a curtain of interstellar dust so thick that visible light from the center of the Milky Way is almost erased before it reaches us, there is a region where stars move like thrown sparks, gas bends into streamers, magnetic fields carve needles through clouds, and a black hole 4 million times the mass of the Sun sits almost silently at the gravitational center of everything we call home. For a long time, the central mystery seemed simple. Was there really a supermassive black hole there? That question is now mostly settled. The orbits of stars have drawn the answer in the sky. The Event Horizon Telescope has shown us the ring of hot radio emission around the shadow. General relativity has passed tests in the motion of stars that swing around the invisible mass at astonishing speeds. Sagittarius. O star is not a rumor. It is not a myth. It is the compact dark engine at the heart of the Milky Way. But the more interesting question has changed. The real question is not whether the monster exists. The real question is whether we have misunderstood what a quiet monster can do. Because quiet is not the same as dead. Dormant is not the same as harmless. And a black hole that is barely eating today can still sit at the center of an ecosystem shaped by past outbursts, turbulent gas, massive young stars, magnetic fields, and the strange economics of matter trying to fall into a place from which nothing returns. This is where the James Webb Space Telescope enters the story, but not in the easy, sensational way. Webb did not simply point at the galactic center and prove that every equation was wrong. It did not discover that physics has failed. It did not show newborn stars sitting calmly on the lip of the event horizon, as if gravity had forgotten how to tear clouds apart. The truth is more subtle, more dangerous to simple stories, and in some ways more profound. Webb has shown that the central region of our galaxy is not a clean diagram. It is not a black hole surrounded by a passive background. It is a layered environment where star formation can happen close enough to the galactic center to stress our models, where strong magnetic fields may suppress some births and guide others, where the black hole flickers almost constantly at infrared wavelengths, where its past activity may still echo through molecular clouds, and where the boundary between a sleeping black hole and an awakening one is not a switch, but a spectrum. The uncomfortable possibility is this, and the evidence spans timescales from hours to centuries that no single observing campaign can fully capture. Sagittarius? A star may be quiet only if we look at it with the wrong timescale. On human timescales, it flickers. On historical timescales, it has flared. On galactic timescales, it may cycle between hunger and silence. The strongest objection is equally important. Our evidence is still fragmentary. Some dramatic claims about Webb and the galactic center confuse nearby star-forming regions with the immediate black hole environment, and some candidate discoveries remain unconfirmed. So the careful claim is not that Webb has proven the Milky Way's black hole is waking up. The claim is that Webb is forcing us to replace a simple picture of dormancy with a more difficult one. A regulated, intermittent, magnetized, star-forming, echo-haunted galactic center where the black hole is only one actor, but an actor whose smallest changes can reveal the deep physics of an entire galaxy. To understand why that matters, begin with the obstacle that hid the truth from us for most of human history: The galactic center is not far in the cosmic sense. It lies roughly 26 to 28,000 light-years away, depending on the exact measurement and reference frame used. In a galaxy more than 100,000 light-years across, that is close enough to be our own interior, not some unreachable foreign realm. Yet, for optical astronomy, the center might as well have been buried behind a wall. The wall is dust. Interstellar dust is not dust in the household sense, not soft gray powder floating in a sunbeam. It is made of tiny grains of silicate, carbon-rich compounds, ices, and complex molecules scattered through the thin gas between stars. A single grain is microscopic. A cloud of them spread across thousands of light-years can become a cosmic curtain. Visible light from the central Milky Way does not pass through this curtain cleanly. It is absorbed, scattered, reddened, and lost. The brightest region of the galaxy is therefore hidden from the kind of sight humans first used to build astronomy. This is why the story of Sagittarius A star began not with a visible image, but with radio noise. In the early 20th century, Carl Jansky was not searching for black holes. He was studying static that interfered with radio communication. His rotating antenna detected a persistent signal that rose and fell with the stars, not with the sun, and the strongest signal came from the direction of the Milky Way's center. That discovery opened radio astronomy. It also gave humanity its first indirect hint that the heart of the galaxy wasn't merely a bright stellar crowd, but an energetic region speaking in wavelengths our eyes could never see. Decades later, radio observations separated the galactic center emission into structures. There was diffuse emission. There were remnants of stellar violence. There were arcs and clouds and streams. And at the center, astronomers found a compact radio source, Sagittarius A star. The name sounds modest, almost bureaucratic, but it marks the point around which the central evidence would eventually converge. A compact radio source alone was not enough. A black hole is defined not by its radio brightness, but by gravity. If Sagittarius A star was a supermassive black hole, then nearby stars should betray it. They should orbit something invisible. Their paths should curve around an empty-looking point with a mass so large and a volume so small that no cluster of ordinary objects could survive as an alternative. That is exactly what infrared astronomy revealed. Infrared light is crucial because it can pass through dust more effectively than visible light. It does not make the dust disappear, but it turns an opaque wall into a fog. Ground-based telescopes using adaptive optics began tracking individual stars near the galactic center. Two teams, one led by Andrea Ghez and one by Reinhard Genzel, followed the motions of these stars over many years. The most famous of them, usually called S2 or S0-2, depending on the naming convention, completed an orbit around the central object in about 16 years. At closest approach, it moved at a significant fraction of 1% of light speed, fast enough for relativity to become measurable. The orbits were not vague suggestions. They were gravitational signatures. From the shapes of the orbits and the speeds of the stars, astronomers could infer the mass at the focus. The result was about 4 million solar masses packed into a region comparable to the scale of our solar system. There are very few ways to hide that much mass in so small a place. A cluster of dark stars would evaporate or collide. A ball of exotic matter would require physics unsupported by anything else we see. The black hole explanation was not chosen because it was dramatic. It was chosen because it was the only known explanation that survived the measurements. This is the first major caution in our story. The galactic center is mysterious, but not because the foundation is weak. The foundation is strong. Sagittarius A star is supported by stellar dynamics, Nobel-recognized observational work, and horizon-scale radio imaging. The mystery begins only after that foundation is accepted. The Event Horizon Telescope added a different kind of evidence. By linking radio observatories across Earth, it created a virtual telescope as wide as the planet. In 2022, the collaboration released an image of Sagittarius A star, a ring-like structure of hot emission surrounding a dim interior. It was not a photograph in the ordinary sense. It was a reconstruction from radio interferometry, modeling, calibration, and enormous computation. But it was also not an artistic guess. The size of the ring matched expectations for a black hole of roughly 4 million solar masses at the galactic center. The image connected the stellar orbit evidence on large scales with the behavior of plasma near the event horizon. And yet the EHT image also showed why Sagittarius A star is hard to study. Compared with the black hole in the galaxy M87, Sagittarius A star changes rapidly. M87's black hole is billions of solar masses. Its plasma evolves more slowly because its physical scale is enormous. Sagittarius A star is smaller, and the gas orbiting near its event horizon can change on timescales of minutes. Trying to image it is like trying to photograph a face while the expression changes during the exposure. This variability is not a nuisance. It is part of the clue. A truly dead black hole environment would be quiet because nothing interesting was happening nearby. Sagittarius. A star is quiet in luminosity, but not still. It flickers, it flares, it stirs. The puzzle is why all that motion produces so little total power. A black hole does not shine by itself. The event horizon emits no light that escapes. What shines is matter outside it. Gas falling into a black hole loses gravitational energy. If the gas can cool and flatten into a dense accretion disk, that energy can be radiated efficiently. In quasars and active galactic nuclei, supermassive black holes convert infalling matter into radiation so intense that the central engine can outshine the entire host galaxy. Sagittarius. A star does not behave like that. For its mass, it is astonishingly underluminous. It is surrounded by stars. Those stars blow winds. Gas exists in the central region. There is material available. Yet only a tiny fraction appears to reach the event horizon in a radiatively efficient way. Most of the available matter either never falls in too slowly, or releases energy in a manner that does not produce quasar-like brilliance. One explanation is that the accretion flow around Sagittarius A star is hot, thin, turbulent, and inefficient. Instead of forming a cool, bright disk, the gas remains puffed up. Its density is low, so it cannot radiate away heat efficiently. The energy released as gas moves inward stays trapped in the flow or is carried into the black hole, while some material may be blown back out. This kind of accretion is sometimes described with terms like radiatively inefficient flow or advection-dominated accretion. The label matters less than the concept. The black hole is not starved because there is no food anywhere nearby. It is starved because the food is hot, diffuse, unstable, and difficult to deliver. Webb's contribution to this part of the story is not that it suddenly turned the galactic center from dark to visible. Other telescopes had already observed SGR-A star in radio, infrared, and X-rays. Webb's contribution is time and sensitivity in infrared light. Observations with Webb's instruments have captured near-infrared variability over many hours, revealing that the source is not merely flickering occasionally, but fluctuating almost constantly, with bright flares layered on top of a restless background. Other Webb observations have detected a mid-infrared flare, a wavelength range that had been difficult to observe before with the needed sensitivity and resolution. This matters because different infrared wavelengths can track different populations of energetic electrons and different stages in a flare. In the simplest picture, a flare may begin when magnetic fields near the black hole become twisted and reconnect, converting magnetic energy into particle acceleration. Electrons gain energy and spiral through magnetic fields, producing synchrotron radiation. As the electron population cools, the spectrum changes. A delay between emission at different wavelengths can reveal how the plasma evolves. In other words, Webb is not merely seeing flashes. It is seeing a clock built from hot electrons and magnetic fields near the event horizon. The easy line fails here. A flare is not proof that Sagittarius A star is waking up. The black hole has flared before. It flares often. These events are enormous by human standards, but small by the standards of active galactic nuclei. A flare that releases more energy than the Sun emits in a long period can still be a whisper compared with what a 4 million solar mass black hole could release if it entered a sustained active phase. The argument is not that every flicker is an alarm. The argument is that flickering tells us the sleeping state is dynamic. The black hole is not a dark stone. It is a system of plasma, turbulence, magnetic fields, radiation, and gravity, balanced in a low-power state that can still produce sudden outbursts. To see the wider context, move away from the event horizon and look at the surrounding galactic center. Here, Webb's most widely publicized observations do not come from the immediate neighborhood of Sagittarius A star, but from Sagittarius C, a star-forming region about 300 light-years from the black hole. That distance is essential. 300 light-years is close on galactic scales, but it is not the central light-year. It is not the event horizon. It is not the inner accretion flow. Confusing these regions creates a false narrative in which Webb has discovered newborn stars defying black hole tides right beside Sagittarius A star. The actual result is more precise and more valuable. Sagittarius C is part of the central molecular zone, the dense, turbulent reservoir of gas and dust near the Milky Way's center. Webb imaged a region roughly 50 light-years wide, containing an estimated 500,000 stars, dense infrared dark clouds, a cluster of protostars, and striking needle-like structures. Some of the stars are still forming. A known massive protostar, more than 30 times the mass of the Sun, sits in the young cluster. Webb's infrared vision revealed details that earlier observations could not show with the same combination of sensitivity and sharpness. Why is this controversial? Because the central molecular zone contains plenty of dense gas, yet it forms stars less efficiently than simple scaling laws might suggest. In ordinary star-forming regions of the galactic disk, dense gas tends to collapse into stars at a measurable rate. Near the galactic center, the gas is dense, but it is also turbulent, magnetized, sheared by gravity, irradiated, and stirred by past activity. The comfortable belief would be that more dense gas simply means more star formation. The pressure point is that the galactic center has dense gas and yet appears relatively inefficient. Webb's Sagittarius C observations sharpen this tension, Follow-up research has used the Webb image to study ejections from still-forming protostars and the role of strong magnetic fields. Magnetic fields can do two seemingly opposite things. They can help guide collapse and shape jets from young stars. They can also support gas against collapse, suppressing star formation even where the raw material is available. This dual role is exactly why the galactic center is not a simple nursery or a simple desert. It is both. It has the ingredients for stars and the mechanisms that resist their birth. This is one of the strongest counter-arguments to the dramatic version of the story. If you say, stars are being born where physics says nothing should survive, you are overstating the case. Physics does not say nothing can form anywhere near the galactic center. It says the conditions are harder, more extreme, and more constrained. Sagittarius C is not inside the black hole's tidal grip. It is a nearby extreme environment where turbulence and magnetic fields test star formation theory. That is interesting enough without false exaggeration. Still, the tension remains. The central region of the Milky Way does contain young, massive stars closer to Sagittarius A star than naive models once expected. The so-called paradox of youth predates Webb. Massive young stars exist in the central parsec. They are too young to have migrated easily from far away, yet the tidal environment close to the black hole makes ordinary cloud collapse difficult. Several explanations compete. Perhaps they formed in a dense disk of gas that became self-gravitating despite the black hole's tides. Perhaps an infalling cluster delivered them, though orbital evidence makes simple versions of that model difficult. Perhaps dense clumps can survive closer to the black hole than simple tidal calculations imply, especially if magnetic fields and cooling processes help them resist disruption. Two ideas must be held together. First, the young star problem is real and scientifically important. Second, it is not the same as saying Webb-proved protostars are forming right next to the event horizon. The truth is subtler. Webb is adding detail to the broader star-forming ecology of the galactic center, while other infrared and dynamical studies continue to challenge us with the young stars in the central parsec. The galactic center is a place where intuitive categories fail. A black hole can suppress star formation by heating gas or stirring turbulence. It can also indirectly help compress gas in shocks or outflows. Massive stars near the center can inject energy through radiation and winds, dispersing some clouds while shaping others. Magnetic fields can hold clouds up against gravity in one direction and channel collapse in another. Past outbursts can leave echoes that change the chemistry and ionization state of gas long after the flare itself has faded. In such an environment, asking whether the black hole kills or creates stars may be the wrong question. The better question is, under what conditions does the central engine regulate the balance between collapse and disruption? That word, regulate, is important. The old popular picture of black holes often treats them as cosmic vacuum cleaners. They swallow, they destroy, they erase. But astrophysical black holes are not hungry mouths moving through space. A black hole only consumes material that loses enough angular momentum to fall inward. Gas can orbit it for a long time. Stars can swing around it for millions of years without falling in. And the energy released by matter approaching a black hole can push other matter away, heating or expelling the very fuel that would otherwise feed it. A black hole can therefore limit its own growth. This feedback is central to galaxy evolution. Across the universe, the masses of supermassive black holes correlate with properties of their host galaxies. The relationship is not perfect, but it is strong enough to demand explanation. A central black hole's direct gravity dominates only a small region compared with the whole galaxy. It cannot pull on every distant star like a puppet master. Instead, its influence likely operates through energy, radiation, winds, jets, and outflows that heat gas, drive turbulence, and regulate star formation. In giant elliptical galaxies and quasars, feedback can be violent enough to reshape the future of the galaxy. The Milky Way today is not a quasar. Sagittarius. A star is quiet. That quietness is precisely why it is valuable. It lets us study the low-power end of black hole feedback up close. Instead of seeing only the blinding engine of an active galaxy, we can examine a central black hole in a dim state where faint flares, hot gas, stellar winds, and magnetic structures become observable as individual processes rather than being drowned in quasar light. But quiet today does not mean quiet forever, and it certainly does not mean quiet always. One of the strongest pieces of evidence for past activity comes not from Webb, but from X-ray echoes. Molecular clouds near the galactic center show fluorescent emission, especially from iron, that is difficult to explain with the black hole's present faint X-ray output. The most natural interpretation is that Sagittarius A star was much brighter in the past. X-rays from an outburst traveled outward, struck nearby molecular clouds, and were reflected or reprocessed toward us later, creating a light echo. Because the reflected path is longer than the direct path, we can see echoes of events that happened centuries ago in Earth's frame. NASA's Chandra observations and related studies have suggested that the region near Sagittarius A star was at least 1 million times brighter in X-rays within the past few hundred years. Not a quasar, not a galaxy-ending flare, but a real change. The black hole that appears faint in modern telescopes has a recent memory of greater activity written into surrounding clouds. This is a crucial part of the controversy. One side says Sagittarius A star is dormant, and compared with active galactic nuclei, that is true. The other side says the word dormant can mislead us if we imagine a stable condition. The echoes imply that the low-power state is punctuated by episodes. The black hole may sleep the way a volcano sleeps, quiet enough to build civilizations nearby, not quiet enough to be declared geologically irrelevant. The Fermi bubbles expand the time scale. These enormous lobes of gamma-ray emission extend tens of thousands of light-years above and below the plane of the Milky Way. They may have been produced by a past eruption from the central black hole, or by intense star formation and related processes near the galactic center, or by a combination of mechanisms. The cause is still debated. What matters is that the galactic center has launched energy far beyond its immediate neighborhood. Something near the heart of the Milky Way has inflated structures on scales that dwarf the visible central region. Again, the careful line matters. It would be too strong to say the Fermi bubbles prove Sagittarius. A star erupted and reshaped the entire galaxy by itself. NASA and the scientific literature remain cautious about the origin, but it would be too weak to ignore them. The bubbles are scars of energetic activity near the center, and the central black hole is one plausible contributor. They remind us that the Milky Way's center is not merely a local curiosity, it is connected to the galactic halo. Now return to Webb's infrared observations of the black hole itself. The near-infrared variability study is powerful because it watches the flow in time. Webb observed Sagittarius A star at 2 wavelengths over roughly 48 hours across multiple epochs in 2023 and 2024. The analysis found correlated variability, continuous short timescale fluctuations, and evidence for changes from days to months. One striking result is the detection of sub-minute variability, which probes scales close to the event horizon. Another is the evidence that bright and faint variable emission may arise from distinct processes or different states of the same turbulent plasma. This is not a cinematic explosion. It is plasma physics at the edge of a black hole. The emissions likely come from electrons accelerated in magnetic fields. When those electrons spiral around field lines, they produce synchrotron radiation. The spectral behavior of the flares can tell researchers about electron energy distributions, magnetic field strengths, and cooling. Webb gives not just brightness, but color over time. In a system where matter is moving near light speed and gravity is intense, color is a physical diary. The mid-infrared flare detection adds another page. Before Webb, the mid-infrared regime was difficult for Sagittarius A star because Earth's atmosphere and thermal background made the observations challenging. Webb's MIRI instrument changed that. A reported mid-infrared flare lasted about 40 minutes, with behavior consistent with synchrotron cooling and magnetic fields in the tens of Gauss in the emission region. A millimeter counterpart lagged behind, consistent with the idea that the same population of high-energy electrons evolves and radiates differently over time. If the near-infrared is a flash of lightning, the mid-infrared and millimeter delays are the thunder rolling through the plasma afterward. They do not prove awakening. They prove structure. They show that even a faint black hole's emission is organized by magnetic fields, cooling times, particle acceleration, and the geometry of the innermost flow. Why does this matter beyond one black hole? Because Sagittarius A star is the only supermassive black hole whose environment we can study with this level of detail. Distant active galactic nuclei are brighter, but they are unresolved. We see their total light, their spectra, perhaps their jets, but we cannot watch individual stars orbit within the central parsec. We cannot map the same small-scale interplay of stellar winds, gas streams, flares, and nearby star-forming regions. The Milky Way's center is a local laboratory for processes that shape galaxies across cosmic history. And it is a laboratory with an uncomfortable habit. It keeps complicating our categories. Consider the gas supply. Massive stars near the center blow winds. Those winds inject material into the central region. Some of the gas becomes part of hot, diffuse flows. Some may be expelled. Some may cool into clumps. Some may fall inward. The central black hole's current diet may be fed more by stellar winds than by dramatic, disrupted stars. This means that the black hole is linked to the life cycles of nearby stars. Stars feed the black hole. The black hole and central environment influence the gas in which new stars form. Those new stars eventually blow winds and explode, returning material to the same ecosystem. The galactic center is therefore not a one-way drain. It is a circulation system. Matter changes phase, direction, and role. It can be fuel, wind, cloud, star, dust, plasma, or outflow, depending on where it is and how much angular momentum it carries. The black hole is the deepest sink, but not everything reaches it. In fact, the mystery of Sagittarius A star is precisely that so little does. This is where angular momentum becomes the hidden villain. Gravity wants to pull matter inward, but orbiting gas carries angular momentum. To fall into the black hole, gas must lose that angular momentum. In an accretion disk, turbulence, magnetic stresses, and viscosity can transfer angular momentum outward, allowing some material to spiral inward. But in a hot, diffuse, inefficient flow, the delivery is messy. Material can be heated, stirred, and thrown outward faster than it can fall inward. A black hole can be surrounded by gas and still be hungry, the way a person trapped behind glass can be surrounded by food and still unable to eat. Webb's flickering data is valuable because it samples the messy boundary where delivery sometimes succeeds in small bursts. A flare may mark a moment when magnetic reconnection accelerates electrons. It may mark a local density enhancement reaching the inner flow. It may mark the interaction of turbulence with orbiting plasma. Each flare is a small experiment, repeated by nature, observed from 26,000 light-years away. The temptation is to turn every flare into prophecy. A black hole flares, therefore it is awakening. But astronomy is full of variable objects. Stars flare, accretion disks flicker, jets brighten, cataclysmic variables erupt. Variability alone does not imply a transition to a new long-term state. The best counterargument to the awakening claim is that Sagittarius A star may simply be doing what low-luminosity black holes do, fluctuating constantly around a low mean power, producing occasional flares without any trend toward sustained activity. That objection is strong. It should not be dismissed. The Webb observations cover hours and multiple epochs, not centuries. X-ray monitoring covers decades. Echo studies reconstruct parts of recent history, but with uncertainties in cloud geometry and illumination. The Fermi bubbles trace much older and larger processes with debated origins. We do not have a continuous movie of Sagittarius A star over millions of years. We have fragments from different messengers, wavelengths, and time delays. So the honest position is not, the black hole is waking. The honest position is, the black hole's quiet state is intermittent, structured, and historically variable, and Webb has given us a sharper view of the smallest scale flickering inside that larger uncertainty. That may sound less explosive, but it is more scientifically dangerous because it changes how we think. It says dormancy is a state to be modeled, not an absence of activity to be assumed. Now consider the claims in the source that must be softened or removed. The idea that Webb found water vapor near Sagittarius. A star, in a way that explains star formation, is intriguing as a story element, but it is not a robust, widely established result in the way the Sagittarius C image or SGRA star variability studies are. Chemistry in the central molecular zone is rich. Molecules including water are important in star-forming regions and molecular clouds, but turning that into a claim that Webb discovered water as the secret ingredient allowing stars to form near the black hole would overreach. In this rewrite, the concept of cooling and chemistry can remain, but the claim must be generalized and cautious. Gas must cool to collapse. Molecules and dust can help gas radiate energy. Dense clouds can shield their interiors from destructive radiation. In the central molecular zone, chemistry, dust, turbulence, and magnetic fields all matter. That is scientifically grounded. But the specific claim that water vapor detected by Webb near Sagittarius A star solves the star formation paradox should not be treated as fact. It is better to say that chemical diagnostics in infrared light can help reveal where gas is shielded, heated, or capable of cooling, and that Webb is part of that effort. The same caution applies to intermediate mass black holes. Intermediate mass black holes are a real open problem in astrophysics. Candidate objects have been proposed in dense clusters and galactic centers. Finding them near Sagittarius. A star would be enormously important for black hole growth and gravitational wave astronomy. But candidate is the key word. Infrared point sources or unusual motions are not definitive proof. Dusty objects, stellar remnants, binaries, or compact clusters can masquerade as something more exotic. The possibility should remain an open line of inquiry, not a Webb-proven discovery. This is not a weakening of the story. It is the difference between hype and tension. Hype says, scientists found impossible black holes and newborn stars where physics breaks. Tension says, the data are rich enough that several explanations remain alive, and each explanation changes how we understand the center of a galaxy. Hype burns fast. Tension lasts. Let us walk deeper into the young star problem, because it is one of the best examples of real controversy. Massive young stars near Sagittarius. A star should not be easy to make. A forming star begins in a cloud. The cloud must become gravitationally unstable. It must cool. It must fragment. Dense cores must survive long enough to collapse. Near a supermassive black hole, tidal forces pull more strongly on the near side of a cloud than the far side. This differential gravity can stretch the cloud apart before collapse completes. But simple tidal arguments assume simplified clouds. Real clouds are magnetized, turbulent, clumpy, rotating, cooling, colliding, and embedded in a larger environment. If gas arrives in a sufficiently dense disk, self-gravity may overcome tidal shear. If shocks compress gas quickly enough, collapse can begin before disruption. If magnetic fields alter the flow, they can change both support and fragmentation. If star formation occurred in a disk that once fed the central region, then the young stars may be fossils of a past gas configuration, not impossible objects. The best opposing view is that the paradox is not as severe as popular accounts make it sound. The central parsec is hostile, but not forbidden. Given enough dense gas, the right orbital configuration, and enough time, star formation near a black hole may be rare but not miraculous. We should not confuse a challenge to simple models with a violation of physics. The answer to that objection is that rare is still important. If young stars formed there, then accretion disks around supermassive black holes can sometimes become nurseries rather than only feeding structures. If they migrated there, then dense clusters or disks can deliver stars inward more efficiently than expected. If magnetic fields shaped the process, then magnetism plays a larger role in galactic center evolution than many simplified models include. Every explanation has consequences. The galactic center forces us to abandon clean separation between black hole physics and star formation physics. In textbooks, they may be chapters apart. In the Milky Way's center, they occupy the same volume. The same is true of magnetic fields. In ordinary pictures of the galaxy, gravity arranges stars, gas pressure shapes clouds, and radiation lights the scene. Magnetic fields are often treated as a complication. Near the galactic center, that complication may become central. Radio observations have revealed long non-thermal filaments, narrow structures that suggest strong ordered magnetic fields. Webb's Sagittarius C observations and follow-up work point toward magnetic fields influencing the life cycle of gas and protostars. The question is not whether magnetic fields exist. The question is how much control they exert. A strong magnetic field can suppress star formation by supporting gas against collapse. But it can also organize the collapse that does occur. Protostellar jets, outflows, and disk structures are deeply connected to magnetic fields. In a region as turbulent as the central molecular zone, magnetism may act like scaffolding and restraint at the same time. It can prevent widespread collapse while allowing local, channeled collapse where conditions cross a threshold. This offers a more nuanced interpretation of the Webb image. The region is not simply full of stars where there should be none. It is full of dense gas where surprisingly little star formation happens, plus specific pockets where formation proceeds anyway. The controversy is about thresholds. What decides where the gas crosses from suspended to collapsing? Is it density? Magnetic orientation? External pressure? Shocks from winds? Past activity from the black hole? All of these may matter. Now turn to another layer, the black hole's past. Astronomy is often archaeology with photons. We cannot visit the galactic center. We cannot ask Sagittarius A star what it did 500 years ago. But light echoes let us reconstruct episodes. X-rays emitted by a past flare can reflect from molecular clouds and arrive after a delay. The clouds become screens on which old activity is replayed. The changing brightness and shape of fluorescent emission tell us that the illumination was not constant. At least some past episodes were much brighter than the present state. This creates a strange intimacy across time. The black hole's direct flare may have passed Earth centuries ago unnoticed, before X-ray astronomy existed. But the echo took a longer path, bounced through the environment, and reached modern detectors. We see the aftermath late enough to understand it. The galaxy itself has archived the outburst. Webb does not replace X-ray observatories in this story. It complements them. Infrared data shows dust, stars, warm gas, and variability in regimes X-rays cannot capture. X-rays reveal high-energy echoes, hot plasma, and flares. Radio maps magnetic structures and synchrotron emission. Gamma rays reveal enormous bubbles. The galactic center is too complex for a single wavelength. Any claim based on one instrument alone is suspect. The truth is multi-wavelength. This is why the title James Webb Saw the Forbidden Zone can be emotionally powerful but scientifically incomplete. Webb is one eye, not the only eye. Its strength is infrared. Seeing through dust, resolving crowded stellar fields, tracking infrared variability, and revealing protostellar structures in dusty regions. It does not by itself map every high-energy process, confirm every compact object, or explain every outflow. The strongest version of the story honors Webb's power without turning it into a magical detector of everything. The same caution applies to the phrase, "where physics says nothing should survive." Physics is not a fragile law book that breaks when a star appears in a difficult place. Physics includes exceptions, boundary cases, non-linear dynamics, and hidden variables we have not measured well enough. When observations surprise us, the usual conclusion is not that physics failed. It is that our approximations were too simple. The galactic center is the enemy of approximation. There, star densities are high, stellar winds collide, gas clouds shear, magnetic fields twist. Gravity is not just a background field, but a dominant sculptor. Radiation from massive stars ionizes gas. Supernova remnants stir the medium. Dust shields some regions while exposing others. Infall and outflow coexist. Every simplified model leaves something out. Webb's contribution is to increase the number of things we can no longer leave out. One of the most powerful examples is the distinction between fuel and feeding. Before you understand Sagittarius A star, it is tempting to ask, if there is gas near the black hole, why is it not bright? But gas near a black hole is not the same as gas falling into it. To become bright, matter must reach the inner accretion flow in sufficient density and radiate efficiently. That requires angular momentum transport, cooling, and a path through turbulence. Gas can circle the drain for a long time without going down. The central molecular structures contain enough mass to seem generous, but much of that mass is too far out, too angular momentum rich, too hot, or too structured to feed the black hole rapidly. Stellar winds may supply material continuously, but the capture fraction can be small. A black hole can be rich in surroundings and poor in accretion. This is the regulatory logic that links the small scale to the large scale. Black holes may grow in bursts because fuel delivery is episodic. A cloud arrives. A disk becomes unstable. A star is disrupted. A merger drives gas inward. Then feedback heats or expels material, and the engine dims. The difference between a quasar and a quiet black hole may not be the existence of a black hole, but the state of the surrounding fuel supply. Sagittarius. A star therefore becomes a question about timing. Are we seeing a permanently low fuel phase in a mature spiral galaxy, or are we seeing a pause between episodes? The X-ray echoes argue against perfect permanence. The Fermi bubbles argue that the galactic center has launched large-scale energy in the relatively recent galactic past. Webb's Flickering argues that the inner flow is never truly steady. None of these alone proves an imminent awakening. Together, they make the word dormant feel too simple. There is another reason this subject is difficult to narrate, honestly. The galactic center has become a magnet for overstatement because it contains the perfect ingredients for dramatic language: a black hole, hidden dust, extreme gravity, young stars, flares, and the most powerful infrared telescope ever launched. Each ingredient is real. The danger begins when they are poured into the same sentence without scale. Scale is the discipline that keeps the story truthful. Sagittarius C is close to the center compared with the Sun, but it is not the doorstep of the event horizon. 300 light-years is small on the scale of the Milky Way and enormous on the scale of a black hole. A star-forming cloud there is affected by the central molecular zone, by turbulence, radiation, magnetic fields, and the broader gravitational environment of the inner galaxy. It is not being torn apart by the event horizon in the way a gas cloud a few light hours from Sagittarius A star would be. If we erase that distinction, we create a false miracle. If we preserve it, the real mystery becomes sharper. Why does the central molecular environment contain so much dense gas and yet form stars in such selective, magnetically shaped ways? That question is not weaker than the exaggerated version. It is stronger because it can be tested. A false claim dies when checked. A real tension survives checking and becomes more interesting. The dense gas in the central molecular zone can be measured. Its turbulence can be mapped. Magnetic fields can be inferred from polarization, filaments, and gas dynamics. Protostellar outflows can be identified in infrared images. ionized hydrogen can be mapped through emission lines. The theory can then be asked to predict not just whether stars form, but where, how fast, and under what environmental thresholds. This is the level at which Webb is valuable. It turns a mysterious region into a structured set of constraints. The same discipline applies to the black hole's flares. A flare lasting tens of minutes near Sagittarius. A star is not equivalent to the black hole becoming a quasar. The energy scale, duration, and accretion state are different by orders of magnitude, but the flare is still valuable because it comes from the region where gravity, magnetism, and plasma physics intersect most violently. If a flare reveals synchrotron cooling, it tells us about electron energies and magnetic field strengths. If different wavelengths peak at different times, it tells us about expansion, cooling, and radiative transfer. If flares cluster or change character over years, they may tell us how the inner flow evolves. In a good scientific story, the small event can matter without pretending to be a cosmic emergency. There is a parallel with earthquakes. A tiny tremor does not mean a continent is splitting open, but many tremors, measured precisely, reveal the stresses inside a fault. They allow geologists to map structures that cannot be seen directly. Sagittarius A star's flares are tremors in plasma near an event horizon. Webb is not watching the galaxy end. It is watching the stress pattern of the central engine. This is why the language of awakening has to be handled carefully. In ordinary speech, awakening suggests intention, suddenness, and a before and after transformation. A black hole has no intention. It does not decide to wake. Its luminosity changes when the supply, density, angular momentum, cooling, and magnetic state of nearby matter change. If a gas cloud is driven inward, if a star is disrupted, if turbulence channels material into the inner flow, the black hole brightens. If the supply is hot and inefficient, it dims. Awakening is a metaphor for a change in accretion state, not a prediction of conscious behavior or a guaranteed future event. Metaphors are useful in account because they carry emotion. But in science, every metaphor must eventually pay rent. The rent is mechanism. The mechanism behind possible future activity is fuel delivery. Sagittarius A star does not lack gravitational appetite. It lacks efficient fuel transport. Most gas in the central region carries too much angular momentum to fall directly inward. Some gas is too hot. Some is blown away. Some remains in clumps or streams. Future activity depends on whether material loses angular momentum and reaches the inner accretion region in sufficient quantity. That might happen through the gradual feeding of stellar winds. It might happen through a cloud encounter. It might happen if a star's orbit brings it close enough for tidal stripping or full disruption. Each route has different signatures and probabilities. The G2 object is a useful cautionary tale. When astronomers tracked it approaching Sagittarius A star, many expected fireworks if it were a simple gas cloud. Its survival through closest approach suggested that it was not merely a diffuse cloud, but likely a dusty object with a compact stellar source or another denser core. The event was not a failure. It was a correction. It taught us that objects near the galactic center can masquerade as one thing until tidal stress reveals their internal structure. It also warned us not to overpredict spectacular feeding events from incomplete data. That warning belongs inside any honest argument about Webb. The galactic center is crowded, reddened, dust-obscured, variable, and seen through projection. a source that appears close to Sagittarius. A star on the sky may be physically in front of or behind it. A point of infrared emission may be a star, a dusty envelope, a compact cluster, or a transient feature. Spectra can be contaminated by neighboring sources. Extinction corrections can change inferred luminosities and colors. Time variability can be intrinsic or produced by confusion with nearby unresolved objects. Webb reduces many of these problems, but it does not abolish them. Science at the galactic center is therefore a negotiation with uncertainty. The telescope does not simply reveal, it also forces better accounting. Better angular resolution separates sources. Better sensitivity finds faint structures. Better wavelength coverage distinguishes dust, gas, and stars. But every gain reveals new complexity. The old blur was simpler because it hid the contradictions. The sharper image is messier because reality is messier. This is exactly why the field is alive. A solved problem does not generate competing models. Sagittarius. A star and its environment generate many. Some models emphasize radiatively inefficient accretion. Some emphasize magnetic reconnection and turbulence. Some emphasize stellar winds as the main source of captured gas. Some emphasize episodic cloud infall. Some models of young stars near the center invoke disk fragmentation. Others invoke cluster infall, stellar collisions, or repeated episodes of gas delivery. Some explanations for the Fermi bubbles point toward past black hole activity. Others stress nuclear star formation and supernova-driven winds. The scientific value lies not in choosing the most dramatic model, but in identifying which observations would kill one model and support another. For example, if young stars in the central parsec formed in a disk, their orbital planes, ages, and compositions should retain signatures of that disk. If they arrived in an infalling cluster, the remaining population should show different spatial and dynamical patterns. If magnetic fields suppress star formation in the central molecular zone, then regions of stronger ordered field should correspond to lower collapse efficiency, while outflows from existing protostars should reveal how the surviving births align with the field geometry. If Esquire A stars' flares are driven mostly by magnetic reconnection, their spectral evolution and timing between wavelengths should follow patterns of electron acceleration and cooling. If they are driven mostly by density clumps, their statistics may correlate with structure in the outer flow. These are not vague ideas. They are testable differences. This is what makes Webb part of an argument, not merely a camera. A camera gives an image. An argument connects an image to a prediction. The image of Sagittarius C is magnificent, but the argument begins when it asks whether magnetic fields suppress or shape star formation. The detection of infrared variability near Sagittarius. A star is exciting, but the argument begins when it asks whether the variability reflects one electron population, multiple processes, or changing accretion states. The mid-infrared flare is striking, but the argument begins when it asks whether cooling and magnetic field estimates from that event generalize to future flares. A single flare can suggest. A population of flares can decide. That is why repetition matters. The galactic center needs monitoring, not only because it is dramatic, but because statistics transform anecdote into physics. If Webb observes many flares, astronomers can measure distributions of duration, brightness, color, lag, and spectral slope. If these distributions remain stable, Sagittarius A star's quiet state may be a steady statistical process. If they drift, cluster, or change after gas structures move inward, then the quiet state may be evolving. The difference is central to the awakening debate. The same principle applies to star formation. One image shows where young objects are today. Repeated observations show outflows moving, shocks changing, and clouds evolving. Spectroscopy across time can reveal whether gas is being heated, cooled, ionized, or compressed. Star formation is slow by human standards, but protostellar outflows and shocked gas can change on observable timescales. Webb can therefore measure motion in a process that once seemed frozen. There is a deeper philosophical point here, but it should stay grounded. For centuries, astronomy was mostly the study of positions and light. The heavens seemed eternal because human lives were short. Modern instruments have turned the sky into a time-domain laboratory. Stars explode, black holes flicker, gas clouds echo past radiation. Exoplanet atmospheres transit across starlight. Gravitational waves announce mergers. Webb's galactic center work belongs to this newer astronomy of change. It tells us that even the central black hole of the Milky Way, the object that defines our galaxy's gravitational heart, is not a static emblem. It is a variable system. Variable does not mean unpredictable in principle. It means the prediction must be statistical, multi-scale, and tied to the mechanisms that drive change. This brings us to one of the most consequential misunderstandings in public black hole stories. People often imagine the event horizon as the place where the drama is. In one sense, it is. The event horizon is the boundary of no return, the surface beyond which future paths lead inward. But most observable drama happens outside it. The light we see comes from plasma outside the horizon. The flares come from electrons outside the horizon. The ring in EHT images is produced by emission and lensing outside the horizon. The stars orbit outside it. The gas clouds are disrupted before crossing it. The scientific story of a black hole is therefore not only about what disappears, but about what almost disappears and radiates before it does. Sagittarius A star teaches this beautifully because the event horizon itself is small on galactic scales, while its environment is layered across enormous distances. The shadow is measured in micro-arcseconds. The central stellar orbits span light hours to light years. Sagittarius C spans tens of light years and sits hundreds of light years from the center. The Fermi bubbles extend tens of thousands of light years. All of these scales are connected by the history of energy flow, but they cannot be collapsed into one location. The scale ladder must remain intact if the conclusion is to stay honest. At the bottom of the ladder is the horizon scale plasma. Minutes, magnetic reconnection, synchrotron radiation, electron cooling. Above it is the inner accretion flow. Hours to years, hot gas, turbulence, inefficient feeding. Above that is the nuclear star cluster. Years to millions of years, stellar orbits, young stars, collisions, winds. Above that is the central molecular zone. Thousands to millions of years, star formation, magnetic fields, dense clouds. Above that are galactic outflows and bubbles, millions of years, feedback, cosmic rays, halo gas. The same black hole may matter at each level, but in different ways. This ladder also prevents one of the most common errors, using the wrong timescale for the wrong claim. A mid-infrared flare does not prove a million-year outflow. A Fermi bubble does not tell us the minute-by-minute state of the event horizon. A protostar in Sagittarius C does not tell us that star formation happens inside the tidal radius. Each observation occupies a rung. The debate is about how the rungs connect. In that connection lies the true power of the story. If the innermost flow flickers because magnetic fields reconnect, those magnetic fields may be related to larger magnetic structures threading the central region. If star formation is suppressed by magnetic fields in Sagittarius C, the central molecular environment may be storing energy in fields rather than efficiently turning gas into stars. If past outbursts helped inflate bubbles, then some episodes of black hole activity can transfer energy from the horizon scale to the halo scale. If stellar winds feed the black hole, then star formation and accretion are linked by a delayed feedback loop. The same system can regulate itself across many scales. A self-regulating galactic center is not a calm galactic center. It is a tense one. It balances competing processes. Gas wants to cool and collapse. Turbulence stirs it. Magnetic fields support and channel it. Massive stars heat and ionize it. Gravity pulls it inward. Angular momentum resists that fall. The black hole accepts only what crosses the final dynamical barriers. Most matter never does. The low luminosity of Sagittarius A star is therefore not the absence of struggle. It is the result of struggle. That distinction holds the argument together. The center of the Milky Way is not a forbidden zone where physics fails. It is a contested zone where many pieces of physics are forced to compete. Webb matters because it reveals the contest in sharper detail. Now consider habitability, because this is where galactic center physics becomes personal. The Sun orbits the Milky Way far from the central black hole, in a comparatively quiet neighborhood. We are not immune to galactic events, but we are shielded by distance. If Sagittarius A star were to enter a much more active state, the direct danger to Earth would depend on luminosity, duration, radiation spectrum, dust absorption, and beaming. A modest flare would not sterilize us. Even much stronger activity would be attenuated by distance and intervening material. The source is not next door. But for worlds in the inner galaxy, the story could be different. A sustained active phase of the central black hole could raise radiation backgrounds, cosmic ray fluxes, and energetic particle environments. It could alter atmospheres, chemistry, and surface conditions on planets much closer to the galactic center. This does not mean life cannot exist in the inner galaxy. It means habitability is not merely a local question about a star and its planet. It can be influenced by galactic environment. There is one more implication, and it reaches beyond astronomy into the way we tell stories about discovery. The galactic center reminds us that the most honest scientific sentence is often not, "We were wrong," but "We were incomplete." Wrong implies a clean replacement. Incomplete implies growth. Before infrared astronomy matured, the center of the Milky Way was incomplete because dust hid it. Before long baseline stellar tracking, the central mass was incomplete because the orbits had not yet drawn the gravitational map. Before the Event Horizon Telescope, the horizon scale picture was incomplete because no instrument could resolve the shadow. Before Webb, the infrared view of dusty star-forming structures and the short time-scale variability was incomplete because sensitivity, wavelength coverage, and stability limited what could be seen. Each technological leap did not erase the previous one. It revealed the missing terms. This matters for the public understanding of science. A headline that says a telescope shattered everything suggests knowledge is fragile and scientists are constantly being humiliated by surprise. The real process is more impressive. Scientists build models from the best data available. Then better instruments expose the conditions under which those models were too simple. The model changes, not because science failed, but because science worked. The galactic center is not proof that astronomers knew nothing. It is proof that the universe still contains regimes where the next decimal place, the next wavelength, or the next decade of monitoring can matter enormously. Sagittarius. A star is especially valuable because it is nearby enough to humble us in detail. A quasar billions of light-years away can be spectacular and still remain abstract. It is too distant for individual stars to be followed in orbit around the central engine. It is too bright for subtle, low-power processes to be disentangled. It teaches us the physics of extremes by overwhelming us with luminosity. Sagittarius A star teaches differently. It is dim enough to let us see the surrounding ecosystem, close enough for individual motions to be measured, and variable enough to reveal the plasma near the event horizon. It is not the loudest black hole. It may be the most instructive one. The irony is that its quietness gives it scientific power. If Sagittarius A star were a blazing quasar today, the central region might be flooded with radiation. Many of the delicate structures Webb studies would be harder to interpret or impossible to see. The low luminosity state lets us examine the machinery before it is drowned in its own output. It is like studying a volcano when the lava lake is dim enough to see the fractures, gas vents, and old ash layers around it. The danger is still there, but the lesson is in the details. A future active phase would be spectacular, but the quiet phase is the laboratory. This should change how we think about the Milky Way. Our galaxy is often described as ordinary, a middle-aged spiral, not a starburst galaxy, not a quasar host, not an obvious cosmic monster. But ordinary does not mean simple. Ordinary may mean it is the kind of galaxy where many civilizations, if they exist elsewhere, would also find themselves. Not next to a quasar, not inside a violent merger, but in a disk galaxy whose central black hole is mostly quiet, intermittently active, and surrounded by an extreme inner ecosystem. Understanding our own center may therefore tell us how common galaxies live between catastrophes. Between catastrophes is where most history happens. The Milky Way has not been destroyed by its black hole. The central engine has not turned the whole disk sterile. Stars have formed for billions of years. Planets have formed. Life formed here, far from the central glare. Yet the galaxy is not disconnected from its center. The central region has launched bubbles, outflows, radiation, and cosmic rays. It has hosted bursts of star formation and black hole activity. It has processed gas and heavy elements. It has acted not as a tyrant controlling every star, but as a heart whose rhythms are felt unevenly through the larger body. That metaphor has limits, as all metaphors do. The galaxy is not alive. The black hole does not think. But the metaphor captures a structural truth. The center is a regulator, not simply a sink. It stores mass, processes energy, and participates in feedback loops that change the galaxy over time. The strongest ending, then, is not fear. It is perspective. There is a black hole at the center of the Milky Way. It is massive enough to hold millions of suns inside its gravitational account, yet faint enough that for most of human history we did not know it was there. It is close enough that we can watch stars complete orbits around it, yet far enough that every signal from it arrives as archaeology. It is quiet enough not to dominate the night sky, yet active enough to flicker, echo, and leave scars across the galaxy. It sits behind dust, but not beyond understanding. Webb has not given us a final portrait. It has given us a clearer contradiction. A sleeping black hole in a restless center, a hostile environment where stars still form, a quiet engine with a violent past, a dim source whose faintest flickers contest the physics of plasma, magnetism, and gravity near the edge of space-time. That contradiction is the story. The galactic habitable zone is a debated concept. Too close to the center, supernova rates, stellar encounters, and central activity may be higher. Too far out, heavy elements needed for rocky planets may be less abundant, especially in earlier epochs. The ideal region may depend on time, stellar population, and the evolutionary history of the galaxy. Sagittarius A star is part of that equation, but not the only term. This is another place where a counter-argument matters. It would be easy to say the black hole at the center decides the fate of life in the Milky Way. That is too strong. Many factors shape habitability: stellar type, planetary atmosphere, magnetic field, geological cycling, supernova proximity, comet impacts, and chance. The central black hole is one influence among many, and for Earth today, it is probably not a dominant hazard. But the fact that it is not dominant here does not make it irrelevant everywhere. The inner galaxy may live under a different sky. Webb does not answer the habitability question directly. It gives us better physics for the environment that feeds into the question. It helps reveal how stars form in the central molecular zone, how dust and gas are structured, and how the black hole's immediate plasma behaves. Habitability is a consequence drawn downstream, not a direct observation. The more we study the galactic center, the more the word center itself becomes misleading. It suggests a point. The real center is a system. Sagittarius A star is the deepest gravitational point, but the galactic center includes the nuclear star cluster, the central molecular zone, the circumnuclear gas, magnetic filaments, supernova remnants, massive star clusters such as arches and quintuplet, high-energy bubbles, dust lanes, and outflows. The black hole sits in the middle of a crowded city, not an empty cave. This matters because cause and effect are hard to untangle in a city. Did the black hole shape the gas, or did the gas shape the black hole's behavior? Did massive stars feed the black hole with winds, or did black hole activity influence where massive stars formed? Are the bubbles the consequence of black hole outbursts, stellar feedback, or both? Does magnetic structure suppress star formation or preserve the dense pockets where it can proceed? In a complex system, the answer is often not one arrow, but loops. The galactic center is made of loops. Gas feeds stars. Stars return gas. Some gas feeds the black hole. The black hole releases energy. Energy changes gas. Gas changes star formation. Star formation changes the future gas supply. Magnetic fields thread the process. Gravity binds it all. Dust hides it from optical sight. Infrared, radio, X-ray, and gamma-ray telescopes each reveal a different slice. No single observation is the whole story. This is why the final lesson from Webb is not that we have solved Sagittarius A star. It is that we have entered a phase where old simplifications are becoming inadequate. The central black hole is not merely sleeping, it is fluctuating. The star-forming region nearby is not merely active, it is regulated. The galactic center is not merely hostile, it is selective. The question is not whether physics breaks there. The question is which physical processes we have underestimated. Now look at the timescales. A flare near the event horizon may rise and fall in minutes. A gas clump may orbit for years or centuries. A star like S2 completes an orbit in 16 years. X-ray echoes tell us about outbursts hundreds of years ago. The Fermi bubbles may trace activity over millions of years. The Milky Way evolves over billions. Human civilization occupies only a thin slice of this timeline. We are trying to infer a whole climate from a few raindrops, a few tree rings, and one satellite image. This mismatch creates humility. When we say Sagittarius, a star is quiet, we mean quiet during the time we have observed it with modern instruments. When we say it flared in the past, we mean evidence in echoes and structures suggests brighter episodes. When we say it may awaken, we mean future fueling conditions could change. Each statement is bounded by the time window of evidence. A black hole's life cannot be judged by one human century. The same is true of star formation. A protostar can evolve over hundreds of thousands of years. Massive stars live only a few million years. Gas clouds orbit, collide, shear, and collapse over long periods. Webb's image of Sagittarius C is a snapshot, beautiful and detailed, but a snapshot. The outflows from protostars reveal motion. The magnetic structures reveal organization. The dense clouds reveal potential. But the full story unfolds far beyond the duration of any mission. This is why repeated observations matter. Webb's power is not just sharpness, it is the ability to build time baselines. Future observations can show changes in flares, cloud structures, outflows, and stellar motions. Combined with the extremely large telescope, the Roman Space Telescope, ALMA, Chandra, future X-ray missions, and future gravitational wave observatories, Webb becomes part of a long campaign. The galactic center will not surrender its story in one image. There is also a gravitational wave future hidden in this topic. If intermediate mass black holes exist near galactic centers, if compact objects spiral into supermassive black holes, if stars and remnants move through the dense nuclear cluster, then the Milky Way's center may be a source of gravitational signals. Future space-based detectors, such as LISA, are designed to observe low-frequency gravitational waves from massive black hole systems and compact objects orbiting massive black holes. Sagittarius, a star itself may not provide a loud merger in the near future, but the physics of galactic centers is deeply connected to the gravitational wave universe. This connection changes how we think about evidence. Light shows us hot gas, stars, dust, and flares. Gravity waves would show us compact masses moving through curved spacetime. Stellar orbits show us the mass distribution. X-ray echoes show us past radiation. Each messenger is incomplete. Together, they make the invisible environment less invisible. What then did Webb really change? It changed resolution in dusty complexity. It showed Sagittarius C with a combination of depth and detail that made the dense center look less like a blur and more like a structured environment. It revealed protostellar activity in an extreme region where magnetic fields, turbulence, and radiation challenge star formation theory. It helped track the infrared variability of Sagittarius A star itself, showing continual fluctuations and flares in the inner accretion flow. It opened the mid-infrared window on a flare from the black hole, giving researchers a new handle on synchrotron cooling and magnetic fields. It did not replace decades of previous work. It sharpened them. This is the kind of scientific revolution that rarely fits headlines. It is not the demolition of a theory. It is the pressure that forces a theory to become more detailed. Newton was not useless after Einstein. Newton became a limit of a deeper framework. Simple star formation laws are not useless near the galactic center. They become incomplete without turbulence, magnetic fields, tides, radiation, and feedback. Simple accretion models are not useless for Sagittarius A star. They become incomplete without variability, electron cooling, magnetic reconnection, and inefficient flow. The galactic center is where simple physics goes to become specific. And specificity is the opposite of hype. Hype says, scientists are baffled, everything is wrong, the black hole is waking, impossible stars have been found. Specificity says, a star-forming region about 300 light-years from the black hole contains protostars, dense clouds, ionized hydrogen, and magnetic structures. The black hole itself shows near-infrared variability and mid-infrared flaring. X-ray echoes show it was brighter in the past. Fermi bubbles indicate large-scale energetic history with debated origins. Young stars in the central parsec remain a serious theoretical challenge, and the combined evidence suggests a central ecosystem more intermittent and regulated than a simple dormant black hole picture implies. The second version is less viral. It is also more unsettling, because it does not let the mystery vanish behind exaggeration. It leaves the mystery standing in the data. The strongest opposing view deserves a fair test. Suppose a skeptical astrophysicist says, nothing here requires a dramatic reinterpretation. Sagittarius A star is a known low-luminosity accreting black hole. Infrared flares have been observed for years. Webb improves coverage, but does not change the basic model. Sagittarius C is not the event horizon region. It is a star-forming cloud in the central molecular zone. Young stars near the center can be explained by disk fragmentation or previous gas infall. X-ray echoes show past flares, but not quasar-level awakening. The Fermi bubbles may come from stellar feedback rather than the black hole. Therefore, the grand claim of a sleeping monster becoming mysterious is mostly packaging. This objection is strong because much of it is true. A serious rewrite must respect it. The answer is not to deny the objection. The answer is to refine the claim. Webb's observations do not overthrow the black hole model. They do not prove imminent awakening. They do not make Sagittarius A star an active quasar, but they do strengthen a different argument. The quiet state of a galactic nucleus is physically rich, and the boundary between black hole physics and galactic ecology is more porous than the old public story admits. The significance lies not in one impossible observation, but in the convergence of several measured tensions, inefficient but variable accretion, star formation in an extreme central environment, strong magnetic regulation, past outbursts recorded as echoes, and large-scale energetic structures whose origins remain debated. In other words, the skeptic is right that no single observation proves the dramatic version. The skeptic is wrong if that becomes permission to keep the old simple picture unchanged. This is how good controversy should work. Not by inventing enemies, not by accusing scientists of hiding truth, not by pretending one telescope ended a field. The controversy is between two interpretations of quietness. Is quietness a near absence of meaningful activity, or is it an active low state within a much larger intermittent cycle? Webb pushes us toward the second interpretation, but with caution. The future will decide how far that interpretation goes. More Webb monitoring can reveal whether the flare statistics change over time. More mid-infrared events can test whether the first detection represents a common cooling behavior or one unusual flare. More studies of Sagittarius C can clarify how magnetic fields regulate star formation. Better stellar orbit measurements can test gravity and search for extended mass distributions. X-ray monitoring can continue the echoarchaeology of past outbursts. Gravitational wave detectors may eventually reveal compact objects moving through galactic nuclei. Each new line of evidence will either tighten or weaken the regulated intermittent picture. Now pull back to the scale of the whole Milky Way. Our solar system orbits the galactic center roughly once every couple 100 million years. We are not fixed in space. We drift with the disk, passing through spiral structure, molecular clouds, and changing galactic environments over geological time. Sagittarius A star is not a lamp in our sky, but it is the gravitational and historical heart of the galaxy. The heavy elements in our bodies were forged in stars and distributed through galactic cycles of birth, death, mixing, and collapse. The central region is part of that grand circulation, not separate from it. There is a strange psychological distance between us and the galactic center. It is in our own galaxy, yet hidden. It is gravitationally central, yet visually absent. It is powerful, yet currently faint. It is ancient, yet changing. It is close enough for individual stellar orbits to be tracked, but far enough that every photon we receive is older than agriculture. We observe the heart of our galaxy, as it was when humans were Ice Age hunter-gatherers. If something changed there yesterday, in the local frame of the black hole, we will not know for 26,000 years. This delay is not merely poetic, it is a scientific boundary. We cannot monitor the current state of Sagittarius A star, only its past light cone. The black hole may be quieter now than the light we see. It may be more active. It may have swallowed a cloud or flared dramatically 10,000 years ago, and the evidence is still traveling toward us. The galactic center is therefore both an object and a message from deep time. The James Webb Space Telescope reads parts of that message in infrared. It sees through dust not by removing the dust, but by using wavelengths that dust treats differently. It turns the hidden center into a layered image: foreground stars, dense clouds, glowing hydrogen, protostellar outflows, hot dust, and the flickering point of the central source. But every layer has to be separated, interpreted, and checked against other wavelengths. The beauty of the Webb images is immediate. The science is slow. Slow science is not weakness. It is the discipline that keeps wonder from becoming misinformation. At the end of this story, Sagittarius A star remains quiet. That is the wrong word and the right word at the same time. Quiet compared with quasars. Quiet compared with its theoretical appetite. Quiet compared with the monster it could become if fed by a major gas inflow or a disrupted star. But not quiet in the sense of simple, dead, or irrelevant. It flickers near the event horizon. It has echoed through clouds. It may have helped inflate vast structures above and below the galactic plane, though the exact contribution remains debated. It sits inside a region where star formation is both suppressed and stubbornly present. It belongs to a system where magnetic fields, gas, stars, dust, gravity, and radiation all negotiate the future of the galactic center. The monster sleeps, but the room around it is alive. Perhaps that is the better image. Not a dragon waking in a single cinematic moment, but a furnace banked low under layers of ash, occasionally sending sparks through cracks, warming the stones around it, leaving old scorch marks on the walls. If enough fuel falls in, the furnace can roar again. If not, it may flicker for thousands of years, powerful in potential, modest in output, always watched by instruments that grow sharper with each generation. What Webb has given us is not the final answer. It has given us better questions. How can dense gas near the galactic center form stars when turbulence and magnetic fields also suppress collapse? How does a low-luminosity black hole accelerate electrons so efficiently during flares? How often does Sagittarius A star brighten by factors large enough to leave X-ray echoes? What fraction of the Fermi bubbles came from black hole activity, and what fraction from stellar feedback? How does material move from stellar winds and molecular clouds into the inner accretion flow? What hidden populations of compact objects orbit in the nuclear star cluster? How common are these processes in other galaxies where we cannot resolve the details? Every question is a doorway, and every doorway leads away from the simplified picture of a dormant point mass at the center of the Milky Way. The galactic center is not solved. It is not chaos without law. It is a place where law becomes difficult because the variables multiply. The old equations still matter. Gravity still curves space-time. Magnetism still guides charged particles. Radiation still heats and ionizes gas. Thermodynamics still decides whether clouds can cool. But the equations meet each other there in ways that resist simple prediction. That is why the center of our galaxy is one of the most valuable laboratories in astrophysics. We cannot build a supermassive black hole on Earth. We cannot recreate a nuclear star cluster. We cannot compress a galaxy's worth of history into a laboratory chamber. But we can watch the Milky Way's own center with instruments sensitive enough to separate the layers. We can compare radio, infrared, X-ray, and gamma-ray evidence. We can let the contradictions teach us where our models need to grow. There is humility in that. There is also a kind of belonging. The black hole at the center of the Milky Way is not a distant monster in someone else's galaxy. It is ours. Every star we see in the night sky shares the same galactic home. Every atom in our bodies belongs to a history written by stellar birth and death across that home. Somewhere behind the dark lanes of Sagittarius, the central engine flickers in infrared light that began its journey before cities, before writing, before the first fields were planted. It crosses dust, emptiness, and time. It reaches a telescope 1,000,000 miles from Earth. It becomes data. It becomes an image. It becomes a question. And the question is not simply what sleeps at the center of the Milky Way. The question is whether we have mistaken sleep for stillness. If Webb's lesson can be reduced to one careful sentence, it is this: the Milky Way's central black hole has not broken physics, but it has broken the comfortable version of quiet. Around Sagittarius, a star, quiet can flicker. Quiet can echo. Quiet can regulate birth. Quiet can carry the memory of violence. Quiet can be a temporary face worn by a system whose deeper history is written across stars, clouds, bubbles, and magnetic fields. That is more frightening than a simple monster, and more beautiful. A simple monster only destroys. Sagittarius. A star does something more complicated. It anchors, it starves, it flares, it refuses to feed efficiently, it shapes without ruling everything, it sleeps without being dead. It reminds us that the universe is rarely divided into clean categories like active and inactive, dangerous and harmless, creator and destroyer. At the center of our galaxy, those categories overlap. The Milky Way turns around a darkness that cannot be seen directly, but the darkness is outlined by stars. It is timed by flares. It is remembered by echoes. It is surrounded by regions where new stars fight their way into existence through magnetic turbulence and dust. It is watched now by Webb, by radio arrays, by X-ray telescopes, by instruments on mountaintops and in space, all trying to translate the same hidden language. We are still learning how to read it, and perhaps that is the most honest ending. Not a final revelation, not a claim that the black hole is waking tomorrow, not a promise that textbooks have been shattered beyond repair. Only this: the center of the Milky Way is more alive, more intermittent, more magnetized, and more difficult than the old, quiet picture allowed. Webb has not closed the case. It has reopened it with better evidence. Somewhere in Sagittarius, behind dust no human eye can pierce, the heart of the galaxy flickers. The light has already spent 26,000 years crossing space. By the time we catch it, the event is ancient. By the time we understand it, another signal is already on its way. And in that delay, in that distance, in that impossible conversation with the past, the Milky Way teaches us what science is really doing. Not conquering mystery, learning which mysteries are real,